Hey, so can everybody see my screen? Yes, good. Okay, so I will give a little introductory lecture to the topic. Maybe I hope will be around 20 minutes. Title is Big Image Data Viewing Challenges and Concepts. Oh, sorry. All right. So, what this session actually will be about mainly is an effort by the OME consortium to make a next generation file format for big image data. So that begs the question, what is actually the current generation file format for image data and why may we need a new one? And we thought it might be nice to start this session with a little chat survey of what you think is the current standard. So I would like to ask every one of you, of course only if you want, to maybe answer these 4 questions in the chat. So you could, if you want, put the name of your institute, but then it would be interesting to hear where people in your institute you think typically store image data. So for us, for example, that would be some group file servers. Then if researchers at your institute need to resave your data in some other format than what they get from the microscope, what would they typically use? So for us, I think it's clearly TIFF. And then the third question is, which software would researchers typically use to view image data? And again, in my case, I think the answer is relatively clearly Fiji. So I would now post, so my answers would be here EMBL, file servers, TIFF and Fiji. And I don't know if you don't mind, it would be really interesting to read from all of you what you think is going on at your places. So I give you a few minutes for that. Oops. No, I lost the chat window. And of course, if you have a question to this, then please ask us if this is not clear. All right, interesting. Thank you. Gothenburg, yes. Okay, that looks. Thank you, Camilo. Interesting. Dominic. All right. Seems to be quite a consent. It's interesting. It's like apparently we all do more or less the same. Homero, yeah, that's also actually interesting. Okay, cool. Yeah, I think that was, or is still, okay, DICOM, yes. That was, I was expecting a little bit, maybe, because I think for more medical, I thought maybe DICOM is also something that we will hear. And Sarah, what software do you use to look at DICOM? For proprietary, okay, I see. Okay, fine. Yeah. Okay, I didn't count. I don't know if we have all, but maybe more or less. I think I will continue. I will read later what I didn't read now. But no, I think that's that's very interesting. And it also means that at least what I will talk about now for the next 10 minutes is not completely irrelevant. Okay, so when we have to think about big image data viewing, actually I realized when I prepared the lecture, we have to think about four things almost separately. So one thing is, where is the data stored, like file servers, hard disks? In which format do you store it? Which software do you use to read it? And then also, what viewer do you use? That's a bit technical, this distinction, but you will see in a second why I made it. So what could be the current standard? And I said here views may differ. I think that is just what I thought, but what I got now from your answers is that not so far off from what most of you would say. So somehow you have some sort of file server, so essentially a hard disk, there's a TIFF file, and then you open it in ImageJ. So I think that's maybe like the most simple standard at the moment. So I want to talk a little bit about this standard and what the limitations of it could be. So I have recorded movies for all of this with a setup here at home. So I used my laptop, and then I had external hard disk, and I actually put a not so big image there, a 4 GB TIFF stack. So things can be 100 times bigger these days easily. And in this case, I try to open it just with ImageJ and a normal ImageJ viewer. So I will start this movie and click on it. And what you see, it takes time, right? So it has to load this whole 4 GB into the RAM of the computer, and that's already a little bit boring. That's why I didn't finish the movie, okay? So this is the first challenge. Even if you could load everything into the RAM of your computer, it might be annoying because it takes a lot of time. So you can, as I guess most of you know, do better in ImageJ. So ImageJ has this idea of a virtual stack reader. So I recorded a movie, so it's the same file, but now I say import TIFF virtual stack, and it's there instantly. Yeah, like, I don't know, 50 milliseconds later, I can look through it. Okay, so why does that work? We have a TIFF image, and TIFF images internally are made of many planes. And this reader library for ImageJ can only read one plane at the time, and it will only read the plane that we currently look at in the viewer. So this is called lazy loading. So that's an important word to remember maybe for the rest of the day. Now, this is nice, but we can only look at these planes. What about if we have our TIFF stack and we want to look, like, for example, from another direction? So not this view, but like, let's look from the side. So if we wanted to do this, then in ImageJ, actually, you can take this line tool, for example. And then there's a command called reslice, and then it allows you to look at your stack like from the side, but along this line. But now what happens is it has to again load all data, okay? Because it has to go through all these planes and load all of the data to generate potentially this view. So that's a problem, right? So we can look very fast along this axis, but we are very slow when we look along this axis. And this is because how the data is stored on the disk. So now we can do a little bit better. And that's by using a different viewer. So I'm reading the data with exactly the same libraries as before, just ImageJ virtual stack reader, but now I open it in ImageJ's big data viewer. And there actually you can tell it, you just press Shift X, in fact, and then you look at the data from the side. And let's look what happens here if we do this. It also loads it, and what you see this is much faster now than before. In fact, it takes 40 milliseconds per set slice in a, relatively short amount of time. You have a side view loaded. Now, what's interesting is if you zoom in, it starts again loading. So there, I think the interesting concept to remember is that good viewers, like big data viewer, they really only load exactly what they can display. And the point here is there's less pixels in the window of the big data viewer than the density of set planes. So it doesn't load all of them, but only a couple, like the ones that it actually needs to render the current view. And that's why it's so fast. So that means if you have a good viewer, even with the same kind of back end, you could maybe look at your data faster. Okay, could we do even better? So if we want to look at this TIFF stack from the side, so in fact, we only need one of these rows. So what I was trying to paint here is this is one TIFF plane. And internally, these TIFF planes are stored in many rows. So here I was painting only 5 of these rows. Now it would be great if we look from the side, we might from each plane only have to look at one of these rows if we could read only one of them and not the whole plane. And this is in fact possible. So a technical term here is you can tell your computer to, it's called seek. So actually on the hard disk, these 5 rows are arranged like this. So they are behind each other. So you tell your hard disk, go there, that's called a seek. And then please read this thing. And I call it now row chunk. And I think this word chunk is also something important for the rest of our practical. So chunk means like pieces of data that are on your hard disk stored in one go. It means they can be read very fast. So this will be an important term to remember for also just practical. One technical comment here is you cannot really control how much your computer reads. It will sometimes read maybe a little bit more, but right now that's not such a big deal. So let's see how that works. So I also prepared this for you. So I now used a different reader library that can actually load only rows from a TIFF file. And then I do the same thing again as before. This is now again much faster. So in fact, this is 100 times faster than before. And that was just by changing the reader to something that is smart enough to not read a whole plane if you don't need it, but only read a small part of the file. Okay, but what about I want to cut this big data set in the other direction, like this, right? So not along these rows. Then, in fact, it turns out I have a problem. Because what I have to do on the hard disk now from all of these rows, I just want to read one pixel, right? I need to read this one, this one, this one, this one, this one. So I have to do this seek thing. And then I cannot only read one pixel. That's another problem. So my hard disk will read a lot of stuff. Then I have to do the seek again. And I have to do this couples of times. And it turns out this is horribly slow. This is actually slower typically than reading just the whole plane. So that means, and this is again like maybe important thing to remember. So the way these TIFF planes are chunked makes it nice, you know, to read only a part of it in a certain direction, but it makes it really difficult to read it in another direction. Okay, so that's an important thing. So that basically doesn't really work. So the take-home messages from this part of the talk should be, so there is this word chunking, which means blockwise data layout on disk. And this is very important because it can speed up partial loading of data significantly. Then the other thing to remember is an optimal chunking depends on your use case. So in which angle do you typically look at your data? So there might be different best options. And the other thing is TIFF, like our current standard, I would say, can do a bit of this chunking as I showed, but it's limited to 2D. So you cannot do this in 3D, which is what you really would like to do. Okay, then, so now we have like introduced the concept of chunks. Another very important concept is the pyramid concepts. And actually, this is also something you can do with TIFF. So, and this is, some people also refer to this as the Google Maps kind of style of saving data. So the idea is you save your data not only once, but multiple times, as is shown here on the left. And then, for example, in Google Maps, if you zoom out, it will not load all the details of, let's say, a small town in the middle of the US if you are actually on a scale where you can just distinguish North and South America. But it will load actually completely different data that is blurred and downsampled. And this is why it's so fast. And only if you zoom in, it will start loading these higher resolution levels. And this is also a really good trick that we want to use in bioimaging. And we do use it. So, and actually the OME people did a great job of making this available in TIFF even. So I have here an example. So I'm opening now one of these pyramidal files in Fiji, and actually what you see is it shows me there's several versions of this thing in the same file with different pixel sizes. And in this case, then I have to choose now which one I load. And I was clicking now of one with a relatively low resolution, as you can see. So I probably, if you look at the pyramid here, I was choosing something rather at the top. And then, but then if I zoom in, I just see pixels, so I lose the fine detail. So that's not really this, like what Google Maps gives me. But again, if we use now Big Data Viewer to open the same file, because Big Data Viewer is in fact a viewer that has this pyramidal concept, then this looks better. So we have the file. This is probably a low resolution, but then if we zoom in, it automatically loads for us from the TIFF file the high resolution. So this is the nice behavior that we would like to have. Okay, so take-home message from this is, so this pyramidal storage, we think is really crucial if you want to work with big image data, if you want to browse it smoothly. And again, TIFF can do it, but it's limited to 2D data. So that brings me already to the end and summary of my talk. So I hope I convinced you we would like to have a new standard, and I think the main problem is that TIFF is only 2D. So we want something that can do 3D chunking and 3D pyramids. And that's something I didn't go into now because Josh will talk about it. We want to have also a file format where all of these things work smoothly, not only on your hard disk, but also in the cloud. And Josh will talk with you about what we mean by that. Okay, so thank you very much. I am happy to take questions, and I think we decided you could just start talking. So no need to put it in the chat. So are there any questions? George, yes? Or Jorge?
Hi there. Just a question: how important have you seen, have you seen it, the availability of multiple channels and related metadata associated to this kind of pyramidal images or other formats for the next gen? Thank you.
Yeah, so I think that's a good question, because I only showed now electron microscopy data with one channel, but I think all of this applies equally to multi-channel, and the answer is yes. So actually, in fact, both the TIFF and the new format will support multi-channel. Thank you for the question. Yeah.
I'll go ahead and share a screen, but if there are any more questions, please don't hesitate to speak up. Just up one. Okay, can you see that okay? Someone nod at me. Thank you. All right. Was that a
Can
question?
I ask a question?
Sure.
Yeah, this
Yes.
this I can't switch on the video.
Yeah.
Sorry. Can the I mean, at the moment you're looking at a kind of high resolution data, but how about I think there's actually demands of multimodal data, and do you think about the image, not the necessary image format, but data format that will include kind of multimodal stuff that we eventually have to deal with, I think?
Yes, very good question. Thank you. Yes, we definitely do. And I will show at the end, so in the last hour, an example of this. And so I think there, the main thing is you need a viewer that does the job. Because, for example, in ImageJ, I think whatever images you need open, they need to have exactly the same amount of pixels and the same size in 3D. And that's for multimodal not good, right? Because you have very different resolutions. Maybe something is a little bit tilted because it was acquired with a different microscope. So there again, my big data viewer actually can do that. So because it has really like a physical space model, and then you can just put many images in there and they can internally have completely different voxel sizes and so on. And the trick is you specify essentially a transformation of how you go from the saved voxel space to the space in which this viewer lives. And this is the way how this can be done. And definitely, yes, thank you for the question. That's something we're working on a lot.
Thanks.
All right, I'll go ahead and get started. But the whole time it counts. You know, if you want to just ask a question, please do. I use the term cloud here somewhat sparingly. So I put it in quotation marks and we'll clear up the difference between cloud and what we really want to talk about, which is object storage, but we'll get there in just a bit. So Christian laid out, you know, as data gets larger, as you deal with more dimensions, 3D, etc., you need all these features in your file formats. You know, in the infrastructure you're using, you need to understand these complex bits to start to work fast enough. The current file formats we have, though, that can do this, TIFF and HDF5 to some extent, excuse me, they're very monolithic. So we're putting more and more data into them. They're getting larger. Having these larger single files actually makes it much harder to share them, right? So that's the tension that we're trying to solve here with the next generation file format. And we'll go through that and look at the various pieces. So I'm just going to take an example, one of our first examples of working with this. It was a very large 2D TIFF, so over 400 gigabytes. And we helped the Journal of Cell Biology publish it back in 2012. It went viral. It was getting many thousand clicks per I think second even. It was an eye-opening experience teaching us that we need to be ready for this type of data usage. Okay. What we're looking at, so what we want to help you all solve are really two use cases. There are probably others for what we're talking about today. So what we experienced with the JCB back in 2012, that was actually a little bit later than that. That was the publication. And even what we see with the IDR today. So everything you saw on day 1 and day 2, there's a certain size at which it becomes very difficult to keep a marrow working. So for example, if someone comes to your marrow and says, I want this entire image, and 100 people do that, the server is going to suffer. And that may actually be a problem that some of you ran into. So hopefully what we're talking about today will help with that. But what I find even more exciting is that even if you don't have an Omero, if all you have is a place to store your data and put it online, this would allow you to share very, very large data. So I will be helping you do this with smaller examples. And then by the end of the day, the example that Christian's showing you will be in the terabyte range. And it's something that you could do yourselves if you have the storage, the technology we're giving you, and then you just need the storage, right? So that's kind of the scope of what we're doing. So let's look at this problem a little bit more in detail. I mean, I think Christian has touched on most of this. Typically, if you're trying to share one of these large files, the only thing you can do is upload it somewhere and let someone download it. So I think over the past 2 days, we heard FTP, Aspera, there's grid FTP. So there are ways to download images, but your user is always waiting on the whole image to download before they can start working with it. If it's local, they can use all the techniques that Christian was showing you to access the pyramids, but accessing it remotely is not possible with anything that you've seen so far today. So the trick, the whole thing we're talking about in these next generation file formats is to take the internal structure of these file formats and break it up. You take each of the pyramids. So if you sum up the first pyramid level, 350 gigabytes, all the way down to the smallest pyramid level of 20 megabytes, you get roughly the 437 gigabytes. And then you take all of these pyramids and you cut them into mini chunks, separate files. I'm not going to follow the chat. If you want to ask me something, you have to do it loud. And each of these is a separate file, a separate object that your users can access separately. So you're in the browser, the user is zoomed out like Christian told you, and then you're only accessing 21 megabytes of data, goes fairly fast, and then your user can zoom in and find the region that they're interested in and just load that. So it allows the same principles that Tishy showed you, but doing it in the web browser, right? And critically, that means many people can access the data at the same time. You know, if you ask your IT, can I provide a 400 gigabyte file and I want 100 people to download it, they're probably not going to be happy with you. If you say 100 people are going to download 20 megabytes, obviously that works much better. So always important to keep your IT happy. So what this gives us is a suite of files that we can talk about. We're not trying to get rid of TIFF and HDF5. Well, what we're doing is adding these file formats called ZAR and IN5, and I'll be showing you examples of those. Because what happened is other people have run into this problem. It's nothing new. The ZAR file format developed in the Python community, in the geospatial imaging community, and IN5 developed in the ImageJ Java imaging community. They're very, very similar. They're very, very simple. And so what we're trying to do is bring them together. There may be other formats that arise like this too, and we'll bring those into the suite of file formats that OME is supporting. But we want you to have for each of these levels of data access that you're trying to provide the right solution. So, if your data is fairly small, it's 2D, by all means, stay with OME TIFF. Everyone knows how to work with it, but they're the performance issues that we've already talked about. If you need to get into 3D, HDF5 might be the thing for you. It gives you a single package that's easy to share as long as it's not too big. The two caveats with HDF5 are currently there's no common specification for the multi-resolutions that Christian told you about. So that'll need to be worked on. And as your HDF5 files get bigger, it becomes slower and slower to write them. Reading them is fast, but writing them can get slow. There are people who are working on that though. And then these next generation file formats really are for remote access of multidimensional large data. And what we're working on is the specification to make them interoperable amongst our community. And critically, and we'll look at the reason for this, since they have so many small files, they're highly parallel. And that's really what we want to get to. Because when working in the cloud, you need to access data differently, right? So that's probably one of the last times I'll use the word cloud, at least intentionally. And now we want to talk about object storage. So what I've done here is I've layered the different types of storage that you might have access to. And we're going to look at how your data flows through them. So most often, most people have their data locally, which means it's sitting on the workstation you're dealing with. And from the bottom, you have the fastest possible access. So if you have a solid state disk, maybe you have a spinning disk at HDD, maybe you have a parallel file system, and then as you start to get into NFS and Samba shares, things are getting slower, right? The data is getting farther away from you. And then you're getting close to remote data. So what people typically think of, well, that's maybe not true amongst this group, but what the general population thinks of as the cloud providers are things like Dropbox and Google Drive and Zenodo. Those aren't really cloud infrastructure, certainly not object storage infrastructure. So you need to be careful if your data is there. I would call that remote storage, but Omero itself is remote storage. You've put your data somewhere else and you're accessing it. And each call to get some of the data is getting slower and slower. And then finally, we have object storage. And these are kind of the commercial providers that we know about in this space: Google Cloud Storage, Microsoft Azure, and especially Amazon S3. We'll talk about S3 quite a bit. There are also scientific providers. So all of the S3 storage that we talk about in the IDR comes from the Embassy Cloud. So EBI in Cambridge has paid for this infrastructure, and they've kindly let us use it. So let's look at what each of these levels mean, or what's the spectrum that you need to keep in mind. More and more institutes are driving their users, their facilities, towards object storage because it's cheaper. These are just very ballpark numbers, but if you can, assume a gigabyte of storage on your file system cost €1, you can get, 100th of that in object storage. For example, when I asked Embassy for S3 storage, as how much do you need? 500 terabytes. Okay, here you go, right? Which is kind of an amazing thing to have possible. That data gets stored redundantly on many servers, so you can actually get a much higher throughput. So rather than getting gigabits per second from your hard drive, you can get terabits of data. But each access of the data is much slower. So these are the type of access speeds that Tishy was talking about. Even if you're just loading a single byte, doing that from your hard drive is very fast. Doing that from the storage that's far away from you gets slower and slower. So orders of magnitude slower. And what these two metrics mean is that really software needs to work differently. It needs to get smarter to know that it's working with object storage. It needs to load data in parallel. It just can't do these single seeks that Christian was talking about. The other important difference between file systems and object storage is that you're writing individual objects, and you can't really change them. Once you've put an object, and here objects are the individual chunks that Christian told you about, they're each immutable in the cloud, and you're not updating them as you go. So you need to plan for how you're going to write your data and not move them around. Okay, so let's look at this kind of in a flow diagram, what you would be doing on a regular basis. Everything that Christian was showing you is basically down here. You have your microscopy file formats that came directly from the scope. You're using this reader that Christian was talking about. Here I've drawn bioformats, the library that we provide, and you're translating the data on the fly and you're accessing it in Fiji or somewhere. And this all goes fairly quick, although it can start to slow down if you don't do it well. If you're working with something like Omero, you upload your data in the format that it was given to you as. And then as you access Omero, the same translation happens on the fly. So every time you read an image from Omero, it's figuring out where it lives on disk for you. And what we're encouraging people to do now is to perform the conversion up front. So try to get into your data into one of these open formats. And if you're sharing via object storage, you want to get it into the next generation file format, upload it up somewhere, whatever large scale storage that you've been provided. And then your users no longer have to perform the translation. So they're accessing the data as directly as possible, right? And that's what we want to make possible. Interestingly, Omero could use the same data. So there's no reason that Omero needs to translate. If you've already done the transformation, you can start teaching your Omeros and your other data management systems to do this and really get everything into the optimal format. Okay, so in the practical, we're only going to focus on this outermost, this newest pathway. We're going to take an image, convert it, move it to S3, and show you how to look at it, right? Just so you have a feel for the basic paradigm that we're trying here. Briefly drilling into the conversion, because we'll talk more about this during the practical. We're using a tool called bioformats to raw. So Glencoe software, the commercial arm of OME, needed to have a fast way to convert data from the proprietary file formats into OME TIFF. So they built bioformats to raw and raw to OME TIFF, which uses this concept of a file format that has many pieces and lets the users transform everything quickly and in parallel, and then take those many pieces and turn it into. But what we're doing here is taking this intermediate format and saying, okay, this is actually the valuable bit. Let's share that. So just briefly, we can talk more in depth later if we want to. And we'll look a little bit into these ZAR files. There are other things that they will enable over time. They are a hierarchy of data, so you can have more than just one image. So someone asked about correlative image data sets. So maybe you want to have both images in the same structure. You want to attach all your metadata. I think there's quite a lot of optimism is what I have in the possibilities of taking this forward as a format for unifying bioimaging. So that's the hope, but even today you can start using it. So where we are in terms of writing the specification, so we've built in, as I mentioned, the multi-resolution, so you can have the large images. We've added specifications for storing your image segmentations in the same structure, if you'd like to. You can also store it in a separate data set. And we've built the specifications for storing high content screening data. And there's a list of next specifications that are coming for storing polygons and meshes and et cetera, et cetera. If you have any ideas of what you would like to save in this structure, let us know. All of that discussion is taking place on Image SC. So if you have any questions about anything we're saying today, or anything about the IDR, or anything about Omero or bioformats, that's the place to ask questions. The specifications are published at this URL. And I'm sorry, I was supposed to add in. So this is the URL for the presentation if you want to click on any of the links. Gleb, let me know if that works, please. And as we add the specifications, what we're doing is using the IDR as a sample, a body of data sets that we can show the world as examples, and those are all available on the S3 from the Embassy Cloud. They're all public, so anything you would like to look at. Thank you, Stefan and Gleb. So I think we're approaching the practical.